Hi guys, welcome to the second part of digital electronics. The first part, which is mathematics, you do it on your own, and I understand you will cover it in your mathematics course. I'll start from logic gates, which are also known as logic elements. So enjoy it. As usual, your digital objectives or your logic gates objectives, please take note of them and make sure you are able to do what is listed. Logic gates, we will first define what is a logic gates, and we'll give some examples. There is a lot that is involved in logic gates. What are logic gates? These are fundamental building blocks of digital system. If you go to your first part, you will see the differences between an analog system and a digital system. A logic gate has got the ability to make decisions in the sense that it produces an output which depends on input combinations. They are electronic circuits, and they can also be used to implement most elementary logic expressions known as Boolean expressions. So we've said it is the basic building blocks of digital systems or of combinational logic. And we've got three basic gates. They are the AND gate, the OR gate, and the NOT gate. And also we've got what we call the universal gates. The two universal gates are the NAND gate and the logic gate. Also we've got the exclusive OR and the exclusive NOR gates. So in this lecture we are going to deal with logic gates, and a logic gate has got some inputs and also some outputs that depend on the inputs. The input can be high or low, true or false, and in that sense it means high and true means the same, while low and false means the same. The input can be on or off, which means on is high, on is true, while off is false or off is low. Or they can be yes or no, open or closed, or simply 1 and 0. So we are using those to define the inputs and outputs. Then we also have got a table which lists all the possible combination of inputs and the corresponding outputs, and we call it a truth table. What does a truth table show? It shows the logic circuit output that corresponds to some combination levels at the input of that particular logic gate. The first gate that we are going to look at is called an AND gate, and you can see the analogy of an AND gate. These are two switches A and B connected in a series. What does that mean? It means that the lamp Y will light when both A and B are high, or when they are on, or when they are 1. So you can go through the literature on your own. So please take note the battery, the two switches that are in series, and our bulb Y. If B is off and Y is on, the lamp will not light. If A is on and B is off, the lamp will not light. If both A and B are off, the lamp will not light. Y will light only when A and B are off. Hence, we have got the name all or nothing, which means all must be on, or else there is nothing at Y. That is an AND gate. It produces a high when all inputs are high, or when all inputs are 1, or when all inputs are true. You choose what you want to use to define high or true or 1. Let's go to the AND gate, a truth table. Before the truth table, that is a symbol of an AND gate, and that is an American symbol. Please take note. And beside it, we are showing the various combination of inputs and our output y. For example, if A is 0 and B is 0, that is the same as saying if switch A is off and switch B is off, it means that light will be off, and we are representing a low or off by zeros. If A is off and B is on is a 1. The lamp Y will not light, hence our output will be 0. If A is on, or if A is 1 and B is off, or B is 0, the output bulb Y will not light. The last combination of inputs, if A is on and B is on, which is the same as saying if A is 1 and B is 1, or if A is true and B is true, the bulb will light, or the output Y will be 1. So let's define an AND gate. An AND gate is a gate that produces an output that is high only and only if all inputs are high. Let me define it again. An AND gate is a gate that has got two inputs, two or more inputs, and produces a high if and only if all inputs are high. Then we've got what we call the Boolean expression. How do you represent the Boolean expression of an AND gate? We say y is equal to a dot b. How do you read that? It is read as y is equal to a and b. You can choose to put that dot, or you can leave that dot. Still, it will mean the same thing. So y is equal to a and b. I will not go through the literature. You go through the literature on your own. So we have looked at the Boolean algebra for an AND gate. We said a and b is equal to y, or y is equal to a and b, where 0 is equal to low voltage and 1 is equal to high voltage. Then we say the Boolean expression is read as a and b, and dot means and. So it's a and b equals the output y. The dot means the function and in Boolean algebra, not multiply as in regular algebra. Sometimes the dot is left out of the Boolean expression. The Boolean expression for a two-input AND gate is read as, or is indicated as, a and b equals to y. That is, the Boolean expression reads a and b equals the output y. For a three-input AND gate, it's a and b and c is equal to y. Please take note of how you read that. Then we have got some laws of Boolean algebra that govern how an AND gate operates, and they are: a and 0 gives you a 0. A and 1 gives you, a and 1 equals to a and a gives you a and not a, or a and bar a is equal to 0. You can take that as, it's not multiplying per se, but you will see that if you multiply a and 0, they'll give you a 0. A and 1, they give you an a, but it's not multiplication per se. So we say these are general statements that are always true for an AND gate, and the AND gate must follow these laws. Not the bar over the variable, like a and bar a is equal to 0. The bar over the variable means not a or the opposite of a. Then the AND operation is performed the same as ordinary multiplication of ones and zeros. That's a summary of the AND gate. Then an AND gate is a logic gate that performs the AND operation of the on the circuit inputs. Rather, an AND gate will be 1 only when all inputs are 1, and for all the other combination of inputs the output will be 0. Then the expression y is equal to AB is read as y equals A and B. Please take note of the summary. The next gate that we are going to look at is called an OR gate, and it is also known as an AND or. And please take note of the analogy of an OR gate. Thus, two switches connected in parallel. And let's analyze the operation of that circuit. If A is closed and B is open, Y will glow. If B is closed and A is open, Y will glow. If both are closed or are on, our current is going to branch and the bulb is going to light. What we were doing is we were already tabulating the truth table, which is shown as A and B being represented by switches and the light being the output. So if A is open and B is open, output will not light. So we have a no. If B is open but Y is on, yes, it will light. Then closed and open, yes, it will light. Closed and closed, yes, it will light. But normally we don't use such a truth table. We use ones and zeros. Please take note. So an OR gate performs an ORing function operation on two or more than two logic variables. What we are saying is an OR gate has got two or more inputs. Then the operation for a two-input OR gate is read as Y is equal to A or B. That is not a plus sign. Y is equal to A or B, read as Y equals to A or B, not as A plus B. Please take note, an OR gate is a logic circuit with two or more inputs but one output. The output of an OR gate is low only when all of its inputs are low. In other words, we are saying the bulb does not light when all the switches are off. For all other possible combinations, the bulb will light or the output will be high. So the output of an OR gate is logic 0 only when all of its inputs are at logic 0. For all other possible combinations, the output is a logic 1. So we can therefore define an OR gate as a device whose output is 1 if at least one of the inputs is high. That is a definition of an OR gate. Please take note the schematic symbol of an OR gate, and as I said, that's an American symbol. And please take note it can have two or more inputs. So the first one is read as Y is equal to A or B. Then the second three-input logic gate is read as Y equals to A or B or C. Let's go to the truth table of a two-input OR gate. Please, in mathematics, that's the way how you count in binary. 0, 0, you get a 0. 0, 1. Please, you can refer to the schematic or the analogy circuit of an OR gate. If A is 1, in other words, if A is off, if A is on and B is off, the output Y will be 1. If both switches are high or if both A and B are 1, it means the output will be 1. That 1 stands for high, or it shows that the bulb will light if we refer to the analog circuit of an OR gate. So that's a truth table of a two-input OR gate. Please take note, you can write inputs on top and also its output on top, but so that you indicate that A and B are your inputs while Y is the output. Then go through that on your own. Right. Then we've got what we call the laws of a Boolean algebra that govern how an OR gate operates. A or 0, you get an A. Please, you must know that by heart. A or 1 gives you a 1. A or A, you don't get 2A, you get an A. A or not A, or A or bar A, you get a 1. Please take note, we'll use those when we do Boolean algebra. So the gate is sometimes called any or gate, which means any of the inputs can be high, or 2 or more of them can be high. It's any or all gate. Please go through the summary. Then the last basic gate we call it a NOT gate, or it is called a NOT gate rather. So a NOT gate is the only gate that has got one input, and the output is always the opposite of the input, or it is also known as inverter. A low input produces a high output, while a high input produces a low output. It produces an output which is always opposite of the what? Of the input. It is also known as a complementing circuit or an inverting circuit. Please take note of the logic symbol. You can see it has got one input that is X, and you can see a bubble at the end of that gate. We call it a not a function. So how do you represent that in using a Boolean expression? It is read as Y is equal to not X, or Y is equal to X bar. Please take note that the bubble can also be put at the input, and the Boolean expression remains the same. X is equal to, Y is equal to X bar, or Y is equal to not X. Please take note of the truth table for a NOT gate. X is the input, Y is the output. So if X is equal to 0, Y will be high, which is a 1. If X is equal to 1, Y will be 0. So the output is always an opposite of the input. The symbol for a NOT gate is that dash, which we call it a bar. So when the input variable to a NOT gate is represented by A and the output by Y, the expression for the output is Y is equal to A bar, or Y is equal to not A. Let's have a look at the summary for the three basic gates: the AND, the OR, and the NOT gate. Please take note. 0 or 0 gives you a 0. 0 or 1 gives you a 1. 1 or 0 gives you a 1. And 1 or 1 gives you a 0. That's the Boolean expression. Then for an AND gate, 0 and 0 gives you a 0. 0 and 1 gives you a 0. 1 and 0 gives you a 0. And 1 gives you a 1. You can formulate for yourself the definition for an OR or for a NOT gate. Then for a NOT gate, the NOT 0 is 1 and NOT 1 is equal to 0, or 1 bar gives you a 0, then 0 bar gives you a 1. Then we've got what you call the universal gates. Why are they called universal? Because they can be used to implement any gate. They can be used to implement an AND gate. They can be used to implement an OR gate, or any type of gate. And the two universal gates are the NAND gate and the NOR gate. The first universal gate that we are going to look at is called a NOR gate, and NOR stands for not or output is noted. Also, an OR gate followed by a NOT gate makes a NOR gate. And also, the truth table for a NOR gate is obtained from the truth table of an OR gate by inverting the output. So the output of a NOR gate is a logic 1 when all its inputs are 0 or are low. For all the other combinations, the output is low or it's a 0. Using a Boolean expression, y is equal to a or b bar. Y is equal to a or b bar, or not a or b. A two-input OR gate followed by a NOT gate is shown. We have got an OR gate, and the output of an OR gate is A or B. Then the output of an OR gate is noted. We have included a NOT gate. So the output of a NOR gate is Y or B bar. Then the logic symbol for a NOT gate, please take note, is the OR gate with a bubble at the output, and please take note of the Boolean expression for a NOR gate. The NOR gate truth table, it has got two inputs A and B, and our output is Y. So we have said we are noting the output of an OR gate so that we have a NOR gate. In other words, 0 and 0 gives you a 1. 0 and 1 gives you a 1. 1 and 0 gives you a 1. Then 1 and 1 gives you a 0. So we have noted the output of an OR gate to obtain 1, 1, 1, 0. In other words, the output of an OR gate are 0, 1, 1, 1. Hence the explanation on the previous. Then the second universal gate is called a NAND gate. Please take note of the schematic symbol. The AND gate followed by a NOT gate is simply helping us to understand a NAND gate, but otherwise it is important to take note of the schematic symbol of an AND gate and not the AND gate followed by a NOT gate. Please, that is an AND gate noted at the output, hence the presence of the bubble. That is a NOT symbol. So NAND stands for not AND. What that means is we are going to invert the output of an AND gate so that we get a NAND gate. An AND gate followed by a NOT gate makes it a NAND gate as shown. Then the logic symbol for a two-input NAND gate is also shown. Please, that is an American symbol. The British symbol uses squares. Please take note. Then the truth table for a NAND gate is obtained from the truth table of an AND gate by complementing, in other words, by inverting the output. The output of a NAND gate is a logic 0 when all its inputs are 1. Let's have a look at the truth table of a NAND gate and also the Boolean expression. The NAND gate operation, also known as the Boolean expression, is Y is equal to A and B and C bar. And this is read as Y is equal to A and B and C whole bar. Whole is showing that A and A, B, C are all covered by the not sign or by the bar. So from the truth table, you can see that the output is 0 when all the inputs are high. Please take note, a NAND gate can have 2 or more inputs. Then we'll go to what we call the exclusive OR gate. Exclusive OR gate, then to the exclusive NOR gate. The exclusive OR gate is also referred to any but not all. Any but not all gate. The exclusive OR gate is often shortened to XOR. Then the exclusive OR gate is sometimes referred to as odd but not even gate. You understand more when we get to the truth table. The term exclusive OR gate is often shortened, that has been said. The symbol, then let's have a look at the logic symbol for the exclusive OR gate. Then the symbol, the plus sign in that circle, shows that the terms are XORed together. So please take note of the schematic of the logic symbol. We call them logic symbols. And please take note of the Boolean expression y is equal x or b. X or b. That's exclusive OR gate. Then the truth table, which is a table that shows the output for any combination of inputs. We have said, let's go to 1 and 1 when our outputs are 1. If we count the number of ones, 1 is an odd number. So we are saying the output is 1 when all inputs are not the same. When all inputs are not the same, or when the summation of ones is odd. That's the definition for an exclusive OR gate. As long as the inputs are the same, the output is 0. As long as the inputs are different, the output is high. So please take note of the exclusive OR output. And please, can you take note of the OR output? The output is high when n or all of the inputs are high. Please go through the literature on your own. Then we have got what to call the exclusive OR. The exclusive OR is very simple to understand, even from the wording. We are adding a bubble or a NOT gate at the output of an exclusive OR gate as shown. Y is equal to X or B bar. Y is equal to X or B bar. Please take note to the truth table, or rather the output is 1 when the inputs are the same. In other words, 0 and 0 give us a 1 and 1 and 1 give us a 1. So please compare the output of an exclusive OR to that of an exclusive NOR. In other words, we are noting the output of exclusive OR to get an exclusive NOR gate. So this is the end of our logic gates. Let me emphasize what is very important. Please, you must be able to define 1. You must be able to indicate the logic symbol. Please, you must also be able to produce a circuit analogous to a particular gate. Please also take note of the truth table. Please, this is the end of our logic gates.